Hi, my name is Sagie Benaim, and today I'll talk about our recent work called Volumetric Disentanglement for 3D scene manipulation. We consider the setting of novel object view synthesis, where we are given a few views of a scene, as well as masks depicting the object to be decomposed, as shown here for the flower. We now want to generate novel views, not only of the full scene, but also of the background and foreground in isolation. Given this decomposition, we can then manipulate the foreground and background in isolation. For instance, we may want to enlarge the TV or semantically manipulate objects volumetrically. We can also manipulate certain volumetric objects in isolation. For instance, the trunk of the tree according to some input text prompt. The main idea is the following. We begin by producing a volumetric representation of the full scene and the background scene. To produce the foreground volume, we then subtract the background from the full scene. We can then manipulate it in isolation, as illustrated by the red box here. Lastly, we can add it back onto the background scene to produce the full volume. Let's begin with the training of the full scene, which follows a similar approach to NERF. In particular, we begin by shooting a ray from a given viewpoint and direction D and sample points X along the ray. For each point along the ray, we predict a color and density value using a neurofield. We then use the density values to predict a weight value for each point along the ray, indicating its importance through a process of volumetric rendering. For a target view, we can consider where the ray intersects this view and calculate the color value for the point as a weighted sum of color values. By shooting different rays, we can do so for every point along a given target view. This gives us all the points along a given view, which we can then compare to the ground truth values. We can then use this loss to update the weights of our neurofield that is lent to map points along the ray to color and density values. We do the same for all training views, and this will give us our full volume that can generalize to novel views as well. Now for the background scene, let's say that it includes only the purple and green object, but not the blue box. We render the given view, but now since the ground truth value includes the blue box, we mask it and only apply a reconstruction loss between unmasked regions. This gives us the background scene. Because of the prior introduced by our network and volumetric rendering, this results in the ability to inpaint the missing regions realistically. So now we have the volumetric representation of the full scene and the background scene. We can now obtain the foreground volume by subtracting, for each point along the ray, the weight of the background from the weight of the full scene, and the color of the background from the color of the full scene. We can now modify the foreground volume by modifying the weights of the color values. In particular, modifying the weights affects depth. We can then add the volumetric foreground object back onto the unmodified background scene by adding the weights and colors for each point along the rays. So let's say we want to transform the foreground object. The inputted linear field are input coordinates along the ray, as well as ray view and direction. By applying a transformation to input coordinates, for instance one of a resize transformation, we can resize the foreground in isolation. We can now add it back to the background volume, which is unmodified, to get back the full scene with the transformed foreground. Using this procedure, we can enlarge the TV, for instance. We can also consider the setting of object camouflage. Let's imagine we have the full scene and the background scene with associated depth maps. Now we may want to fix the weight, that is, fixing the weight of each point along the ray of that of the foreground, while also optimizing the color of each point along the ray to that of the background. This will then give us a camouflaged object. How about semantic manipulation? Let's say we want to modify the blue box to become red. First, we would like to ensure that the background is unchanged. To do this, we render the background for a modified volume and for a fixed volume, and use a reconstruction loss between the rendered backgrounds. Now for the foreground, we render the modified volume and use a mask to ensure only the foreground object is modified. We add the masked foreground to the background from the fixed unmodified volume. This results in an image. We then use a multimodal similarity loss to compare the resulting image to a target text. Without going into details, this loss gives a loss score for images and texts that match semantically and low score otherwise. This results in the ability to manipulate objects volumetrically, as you can see here for different examples. We consider a user study where we ask users to rate from a 1 to 5 how realistic is the resulting object or scene. As can be seen, our method is superior to baselines. In a second user study, we ask users to rate from a 1 to 5 how well was the object removed, extracted, or manipulated. As can be seen, our method is superior to baselines. For object inpainting, we also consider the LPAPES and FID scores, where we achieve comparable or superior performance in comparison to other 3D-based inpainting methods. For object manipulation, we consider the clip similarity, where our method is superior to baselines. To conclude, we provide a volumetric disentanglement framework whereby we can disentangle the foreground and background from the full scene, and whereby we can then render novel views both on the foreground and background in isolation. This enables many downstream tasks, such as 3D object camouflage, non-negative 3D inpainting, 3D object inpainting, 3D object transformation, and 3D text-based semantic manipulation. Thank you for your attention.